Okay, can you hear me? All right. So my name is David Elkouss. I come from Delft, from a group called Quantum Internet and Networked Quantum Computation. So our ambition is to build the first quantum internet. And I would like to share with you our excitement because we believe that we are in a moment analogous to the original classical internet. So I would like to ask you to go back in time to the 29th of October of 1969. So a little bit earlier, DARPA, the American Defense Department, has realized that it was extremely inconvenient to try to transmit information between different quantum classical computers that were not linked with each other. So for instance, we could imagine that there was some computer sitting in Stanford University. It was linked to a computer in UCLA, and then there was another computer also in Stanford University linked to University of Utah. And if in Stanford you receive a message from Utah, then basically you need to take that message, copy it to the other computer, and send it to UCLA. So it was extremely inconvenient. So what they decided to do is to create a network that would allow to efficiently transmit information between these different universities. So they made some call for proposals, and a few companies and a few universities decided to create this first network. So then flash forward to this 29th of October of 1969. They have built some sort of prototype, and they are ready to test it. So of course, they are testing, so they expect it to fail. So they're also using the phone in order to test it. So there's these two guys here. This is, I believe, Charlie Klein, and this is Bill Duval. So Charlie Klein is sitting in UCLA, and he wants to transmit some message to Bill Duval that is in Stanford University. So then he picks the phone and he says, oh, I'm going to try to send you this very sophisticated message, login. Let's see if we succeed. So then he types an L, and then he calls and says, hey, Bill, so what did you see? Oh, did you see the L? And he says, yeah, we see the L. We see the L here. So then he goes on, and he types an O and asks over the phone, so what happened with the O? Did you see it? Yeah, we see it. And then he types the G, and the system crashed. So this is somehow the kind of quantum network that we believe we are ready to implement in the near future. So what will be the quantum internet? So the quantum internet will be some global network that will run in parallel to the classical internet. It will not supersede it. And in each of the nodes, we will have a quantum computer, maybe big, maybe small. And these nodes will be linked by some quantum channel. Whenever the distance is too large, there will be a quantum repeater. And via the magic of some resource that's called entanglement that we will discuss long during this talk, then it will also be possible to create something called a virtual quantum channel between any two nodes in this network. So you might say, oh, so this looks extremely complicated and probably also extremely expensive. So why would we want to build this quantum internet? So we want to build it because it turns out that if we compare what we can do with quantum network and with what we can do with classical network or with classical resources, we have some qualitative advantages for implementing many tasks. So of course, there's communication tasks. I imagine that many of you are already aware of quantum key distribution, but it's not the only communication task that we can implement with advantage with respect to classical networks. We can also do secret sharing, anonymous transfer, clock synchronization, or distributed consensus. And even perhaps not so evident, it turns out that a quantum internet would have extremely strong applications in computation. So for instance, we can think that if we have very precise but small quantum computers, we can link them via a quantum network and build a larger distributed quantum computer, analogous to what we can do nowadays with small chips that we could link and convert into some cluster that is much more powerful than the original chips. And another very interesting application is access to a quantum server. So we can imagine that in some years we will have some quantum computers, but of course, the most powerful computers will not be available to everyone. So we could assume that in some universities we will have some small quantum computers, and perhaps in some companies some much more powerful quantum computer. So if we had a quantum internet, what we could do is to do some computation on the small quantum computer, and once we ran out of power, we could transmit the state we are processing to the quantum server. The quantum server would end the computation and would send it back to us. And it's also very interesting because quantum information allows us to prepare the state and the computation in such a way that the quantum server could learn nothing of the computation or of the state, and in such a way it could be completely secure. Okay? So I've promised you many tasks, but you're saying, so what's the relation of quantum with all these tasks? So why does quantum help, or how does quantum help? So the key is this very unintuitive resource called entanglement. So entanglement is a kind of extremely strong correlation in such a way that if we have two particles or two boxes that are entangled, so it's a correlation, so it does not allow for communication, but it will have some sort of correlation that we cannot replicate with classical bits. So let me give you some sort of intuition. So it will turn out that if two boxes are entangled, then even if they are extremely separated, you could think of some shared random coin, for instance, so that it will have not predetermined answers to the questions we are going to pose, but whenever we pose a question to one of the boxes and it gives an answer, the other box will always give exactly the same answer. So here we have Leia and Luke, and maybe they are going to ask to the boxes. Maybe Leia is going to ask, shall we attack today or tomorrow? And then the boxes will answer, I don't know, let's say today. And then whenever Luke asks the same question, he will be guaranteed he's going to have the same answer that Leia had. But it's difficult to transmit without equations how these strong correlations work, but the key thing is that these boxes will give these exact same answers to very different questions. So we could think that now we ask something completely different, so rice or noodles, and then maybe they are not going to answer what we want, but they will answer the same. And the thing is that also Leia and Luke, they could be in different galaxies, right? But this entanglement will guarantee that this change in the answer will be instantaneously, no matter how separated Leia and Luke are. And another really amazing thing is that entanglement is private, or is monogamous. So if Leia and Luke are entangled, we are guaranteed that no other particle in the universe can be entangled with either Luke or Leia. So it cannot be that there's a third box that perhaps is in the hands of Darth Vader, such that if Leia asks rice or noodles, and the box answers rice, also Darth Vader will learn that the answer was rice. So entanglement is private, and we will see that this is, of course, an extremely convenient feature. So okay, you might think, oh, so he's saying all these things, but this cannot be true, right? And you are in very good company. So famously, Albert Einstein, together with two colleagues, Podolsky and Rosen, in 1935 said, okay, so quantum mechanics is great. If we follow the mathematics, it will predict that this kind of entanglement exists. But surely, he called it spooky. This spooky action at a distance cannot be true. It's certainly that quantum mechanics is not the real way to model reality. But you also can imagine that in the 1930s, we did not have the amazing control of quantum engineering that we have today. So this was sort of a philosophical discussion, and it somehow was left for philosophists. And so people were aware of these predictions, but they didn't know what to do with it, until 30 years later, John Bell said, well, maybe I also don't believe in this entanglement, but I can prepare some tests that will allow us to know if reality is compatible with this entanglement or is not. Or maybe all the correlations that are possible are our very familiar correlations that are, I don't know, having a shared coin, or this kind of correlations. So now, please bear with me. This is the most technical slide that I have for you today. So I want to give you a flavor. Well, not a flavor. This is really the game that Bell proposed. So we have Leia and Luke. Maybe they have communicated in the past, but now they're extremely separated, so perhaps in different galaxies. And then we are going to have some intermediate entity, some referee, that is going to ask some question to Leia. Is this working? So some question to Leia, and some other question to Luke. My bad, yeah. We always talk about Alice and Bob, but I thought it would be more fun with Leia and Luke. So these questions will be binary, so we could think, for instance, that sometimes he will ask to one of them this rice or noodles question, and perhaps he will ask some other times the attack today or tomorrow question. And then Leia and Luke will produce also an answer that will also be a binary answer. So it will be yes, no, today, tomorrow. We can also encode it into a 0 or a 1. And this is called a game because there are some conditions for winning. So we say that if Leia and Luke produce answers such that they verify this equation, so x times y is the same as a plus b mod 2, then they win the game. And if their answers do not verify this equation, then they lose the game. And it's extremely easy to prove that if Leia and Luke only have access to classical resources, then they cannot win with a probability larger than 75%. However, if they share this spooky entanglement, then they can win with probability 85%. So now imagine that you go to the lab and you prepare some setup, and in that setup, this Leia and Luke win with, I don't know, consistently 80% probability. So then they surely have something that is not compatible with our classical understanding of reality. So to be honest, this does not directly allow you to conclude that you have entanglement, but definitely it means that what we call classical correlations are not compatible with what we are saying. And then after John Bell proposed this game, nothing happened. Right? So again, we didn't have the technology appropriate for playing these kind of games, and we needed to wait until the early 1980s for seeing the first, oh, thank you very much, the first experimental implementations of Bell's game. But these implementations were also, for technological reasons, not completely perfect. Maybe some of the time, Leia would not answer anything, and then what do you do? So you can ignore those rounds and say that they are winning with probability larger than 75%, but if you are completely rigorous, then you will say, oh, maybe Leia is just discarding the questions that she doesn't like, such that they can win with probability larger than 85%. You cannot conclude anything. And also maybe in the real experiments, Leia and Luke were not galaxies apart, but maybe they were 2 centimeters apart, right? So maybe they were communicating. Maybe this question was known to Luke, and then this game is not that difficult to win anymore. You can even win with probability 1. So until 2015, there was no implementation of this game that was truly convincing, because they have either any of these two problems. Until in 2015, in Delft, we managed to implement for the first time one of these games of Bell, where there was not the possibility that nature was playing sneaky games on us and was using these rounds where Leia was not answering in order to conceal that she could not win with probability larger than 75%. So somehow, what we must admit is, even if it's very unintuitive like Einstein thought, apparently this kind of strong correlation is possible in nature. OK, so now let's go to application. How we are going to transform these strong correlations into something useful. So let's remember the problem of secure communication. So we have Leia here. She wants to send some letter to Luke. And she wants to send it in such a way that Darth Vader learns nothing about the letter. So what does she do? As we all know, so what she's going to do is she's going to put it in some safe. She's going to close the safe with some key, and she's going to send the safe to Luke that holds a copy of the same key. So is this secure? How do we know? So we don't really know, right? So in practice, what we are going to do is to use not a safe, but a function, and the key is going to be a string of bits. So what Claude Shannon proved already in the late 40s is that this a scheme can only be secure if the key is as long as the message and is used only once. OK, perfect. So now we can send secure communications, right? Except that how do we distribute these keys on the first hand, right? So if we can securely distribute keys, then we don't need the keys for anything, right? It's sort of a circular argument. So basically, even though we know this fact since already 65 years ago, the schemes that we use every day are not secure in this strong sense and are only secure because we believe that there are some problems that are very difficult, for instance, factorizing numbers or computing discrete logarithms. But we only believe that these problems are difficult. There's no one that has proven that these problems are difficult. So we don't really know if the communications that we believe secure every day, I don't know, for accessing our Gmail accounts or communicating with the bank are truly secure, or the NSA is tapping everything, right? We cannot know. And then, as you've also guessed, I guess, from my description of the private characteristics of entanglement, we can create keys with quantum. So the first person to realize this was Steven Weisner in the late 60s. He wrote a paper about this. In 1970, it was a little bit of a different topic. It was about creating banknotes that could not be tampered with. But in any case, the tools were very similar to the tools that would be later used for quantum key distribution. Here's what he recounts about the success of his paper that took 13 years to be published. He said, oh, I showed it to this big shot, showed no interest at all. I showed it to several other people, and they all pulled a strange face and went straight back to what they were already doing. So it was completely ignored. It took 14 years until Bennett and Brassard proposed a protocol for key distribution and coin tossing in some mildly obscure computer science conference. Again, nothing happened, right? The community ignored this and some sort of theoretical amusement. And then 7 years later, Arthur Eckert proposed another method for doing quantum key distribution based on Bell's theorem, which is basically what I've told you a little ago. So how does this work? So you can, I guess, already guess how it's going to work. So you can generate end-to-end entanglement between Luke and Leia many times. Then you can test playing this Bell game if Leia and Luke are entangled using a little bit of disentanglement. And if the test succeeds, if they are entangled, then you can ask the questions. And since the answers are going to be random, you can use them for a key. So these are the two properties that are going to guarantee that you have a key and that the key is secret, right? So we have this maximum correlation, so the key is random, yet Leia and Luke are going to end up with the same key. And then this key is really a key, is private, right? So if Leia and Luke are entangled, no one else, in particular Darth Vader, can know anything about the key. All right, so still, even after Arthur Eckert proposed his protocol and it was published in a nice physics venue, still it was seen as some theory thing outside of real implementation. And 1 year later, Bennett Brassard, together with some other people that could become famous names in the field, did the first implementation of a QKD, of a quantum key distribution protocol. And I also like to quote, to read this, it's very interesting. So this is Brassard writing, I don't know, 5 or 6 years ago, recounting the early days of quantum key distribution. He says, it remains a mystery to me that this successful prototype made a world of a difference to physicists who suddenly paid attention. In particular, it gave us the opportunity to publish in Scientific American. The funny thing is that while our theory had been serious, our prototype was mostly a joke. Indeed, the largest piece in the prototype was the power supply, needed to feed in the order of 1,000 volts to Pockels cells used to turn photon polarization. But power supplies make noise, and not the same noise for the different voltages needed for different polarizations. So we could literally hear the photons as they flew, and zeros and ones made different noises. So our prototype was unconditionally secure only against any eavesdropper who happened to be deaf. OK, so this first prototype that was not very useful somehow caught the public attention, and the field became a field. So what's the state of the art nowadays? So nowadays, you can call this company or several other companies, and you can buy equipment for doing key distribution. This commercial equipment will allow you to distribute keys between parties that are separated 100 kilometers. If instead of using commercial equipment, you tune your devices in the lab, then you can go 300 kilometers. But for fundamental reasons, basically that the losses in fiber optics are exponential, we cannot go farther than this without something called quantum repeaters that I will introduce in a moment. So nowadays, if we want to go farther, we use this thing called trusted repeaters that is basically some glorified way of cheating. So imagine that you have these two very distant nodes. Then what you can do is to place many intermediate nodes, and all the intermediate nodes are going to distribute a key between them. And then basically, if you trust all the intermediate nodes, then you can get a key secure between the end parties, basically by doing an XOR of all these keys. And this is being done in practice, and we have very big networks that allow to do this trusted quantum key distribution. And very recently, we have had a very new kind of development. So July 2017, the Chinese group of Jiang Pan, I don't remember the second name, managed to distribute entanglement between two cities that were at a distance of 1,200 kilometers. This is really, really nice. On the other hand, we cannot truly expect that in the future we are going to have satellites pointing to each of our houses, right? So this will probably play a big role in a future quantum internet, but it cannot be the only block, let's say. So we also need to improve these fiber optic systems if we hope to have a quantum internet. So what stops us from going beyond? So there's this funny property that is completely fundamental, that we cannot copy quantum information. So it's not that our technology forbids us from doing that, but it will allow us in 10 years from now. We can prove mathematically that we can not have a machine that can copy an unknown quantum state. So this is one thing. And the other thing is that current quantum processors can only hold a few quantum bits. So normally, what you would do in classical networks is you would add some redundancy such that you can correct for noise. And that is the way that one can tolerate the different noise in classical communications, right? So we cannot do this, at least currently, in quantum channels. Unfortunately, or fortunately, entanglement will again help us overcome this problem. So this is what we cannot do, direct transmission. So imagine that Leia wants to transmit some unknown quantum state psi to Luke. So she could place it in a quantum channel. Quantum channel is just fiber optics. You can always think fiber optics, that's a quantum channel. But as soon as they are separated a few kilometers, the probability that Luke receives the state will be extremely small. So basically, since Leia cannot copy the state because it's impossible, this is bound to fail, right? So this is not going to allow us to build scalable networks or links. But we can try to send quantum information in a different way. This is called teleportation. So we can imagine that Leia and Luke use their quantum channel to distribute an entangled pair. So if they succeed, great. If they fail, they can try again. Nothing happens. And once they succeed, what Leia can do is to jointly measure the states she wants to transfer with her part of the entangled pair. So if you want to put it in more understandable words, Leia can ask a joint question to these two states, her part of the entangled pair and psi. she will obtain an answer, and that answer she can transmit to Luke over the classical channel. And with the help of that answer and his half of the entangled pair, he will be able to reconstruct psi. Of course, I told you that you cannot copy information, right? So that means that when Leia does this joint question, she will destroy her state. There will be no copying. So once she does this measurement, she will lose the state. And if she transmits the measurement outcome to Luke, Luke will be able to recover it. So this is how we think transmission of quantum information is going to look in quantum networks. OK. And now with this trick of teleportation, we can also construct quantum repeaters. So how so? Imagine that we have this very long chain with 3 nodes. Then what we can have is that the first node shares an entangled pair with the second one, and the second one with the third one. Imagine that the Leia is here, Luke is here. Leia wants to transmit some state psi to Luke. So what they can do is this node is going to teleport the state of this quantum state here to Luke. And then they will have created an entangled pair between Luke and Leia. And now Leia can teleport his state psi to Luke. And again, it has the nice robust properties of the teleportation protocol that I described before. So basically, all this process is unrelated to psi. So whenever they fail, they can try again. The state psi will not be affected by this preparation of the link for teleportation. OK, so now I would want to end saying that maybe you think that all this is a big physics problem. It is, but it's also a big problem in many other ways. So there are many challenges that maybe we had not thought a few years ago, and now that we are really trying to build these networks, we are realizing that many other, perhaps, let's say, classical information or classical network problems that we also need to solve. So here we have your very familiar IPv packet header, and here we will have the payload. So that's very nice. That's how you transmit, let's say, information in a classical network. But here I circle payload, right? So now imagine that you are trying to send quantum information. So this payload is quantum. So the payload goes through a quantum channel, and this goes through a classical channel. So how do you guarantee that the header is linked to the payload? Well, how do you do that? So there are many of these types of problems that are purely classical that will probably mean that we will need to develop some sort of new protocol stack in order to transmit quantum information over networks. So this kind of problem does not exist if one has a point-to-point link, right? But once one goes to go beyond, then this becomes a problem. Another problem. So imagine that this node here, green, wants to send quantum information to this blue link here. So now we know that we need to do this teleportation thing. So basically what you're going to do is to look for some connected path. Let's assume that all these links here mean an entangled pair. So you're going to look for some connected path that will link you to the blue node here. And if you find it, then basically you can teleport 1 qubit at a time until you create an entangled pair between the two end nodes, and then you teleport. That's great. But once you do that, basically you have consumed all these links. These links have disappeared. So somehow the topology of the network is going to change. So when we think about routing protocols, they are going to have a completely different flavor to the routing protocols that we know today. This is, again, a classical problem. There's no quantum here, but we need to think about routing protocols for quantum networks. And last but not least, a very, very annoying problem. So imagine that you have come up with a nice protocol for your classical network, and yeah, you want to implement it and put it, I don't know, in work in some real network. Then the people managing that network will tell you, OK, but does this work? Have you tested it? And you'll say, oh, yes, yes, yes. I went to my favorite network simulator, for instance, I don't know, NS3, and I implemented this network protocol, and everything works great. So yeah, you can implement it, and nothing is going to happen. You are not going to destroy your network. what happens with quantum networks is completely different in the sense that simulating systems has an exponential complexity with a number of quantum bits. So perhaps this prefactor is very mild and you can simulate very large quantum systems. No, that's not true, right? So this is the latest record in simulating quantum systems from April 2017. So basically, we can simulate systems with 42 quantum bits. So now you can imagine that even if our nodes are not very powerful and each one holds, I don't know, 5 or 6 quantum bits, as soon as you have 500 nodes in your network, that's like 2,500 quantum bits in your system. So there's no way that you can simulate its behavior. So that's a big challenge, right? So you can come up with protocols, but then their validation is going to be tremendously challenging. And yeah, this is a problem that we are trying to solve in many different ways, like partial simulation, not of the complete quantum dynamics. But in any case, this is a nice and new problem that we need to solve if we want to build the quantum internet. So this is it. So we think that we are going to manage to solve all these problems, at least to a certain degree, such that in 2020, we are going to build a quantum network between 4 cities in the Netherlands: The Hague, Delft, Amsterdam, and Leiden. And all these nodes in the network will be able to share entanglement, and we will be able to implement many of these protocols that I described at the first of my presentation, but not in a ad hoc way. We will program them in a universal way via some stack of network protocols. So if you're interested in sending login in 2020, then you can join us virtually or in reality. So we have lots of information here if you want to learn more. So you could learn in our free online MOOC if you're interested. You could join our MSc courses if that's what you're trying to do right now. We also have a blog, and not only us, there are tons of information about quantum networks or quantum information right now available to you. If you're curious about the institutional stand of this kind of project, so right now we are joining joining forces with many of the most important players in Europe, and building what we call a little bit pompously Quantum Internet Alliance. And that means that there are many other people in Europe also interested in this sort of project. So yeah, so this is our vision. If you have any question, I'm here to answer them. Thank you very much.